I'm Shweta. I taken the topic of solutions to common parallel programming problems. Here the main topics included is too many threads, data races, deadlocks and live locks, heavily contended locks, non-blocking algorithm, thread safe functions and libraries, memory issues, cache related issues, pipeline stalls, data organization. First, coming to too many threads, it may seem that if a little threading is good, then a lot must be better. In fact, having too many threads can seriously degrade program performance. The impact comes in two ways. First, partitioning a fixed amount of work among too many threads gives each thread too little work, so that the overhead of starting and terminating threads swamps the useful work. Second, having too many concurrent software threads incurs overhead from having to share fixed hardware resources. Time slicing ensures that all software threads make some progress, otherwise some software threads might hog all the hardware threads and starve other software threads. The most obvious overhead is the process of saving and restoring the thread's register state. Suspending a software thread requires saving the register values of hardware thread, so the values can be restored later. Then when the software thread resumes on its next time slice. A more subtle overhead of time slicing is saving and restoring a thread's cache state. Modern processors rely heavily on cache memory, which can be about 10 to 100 times faster than main memory. Caches are fast but finite. When a cache is full, the processor must evict data from the cache to make room for new data. The net effect is that too many threads hurt performance by fighting each other for cache. A similar overhead at a different level is thrashing virtual memory. Most systems use virtual memory where the processors have an address space bigger than the actual available memory. Virtual memory resides on disk and a frequently used portion are kept in real memory. Each software thread requires virtual memory for its stack and private data structures. The cache and virtual memory issues described arise from sharing limited resources among too many software threads. A very different and often more severe problem arises called convoying, in which software threads pile up waiting to acquire a lock. The problem is even worse if the lock implementation is fair, in which a lock is acquired in first served order. The solution that usually works best is to limit the number of runnable threads to a number of hardware threads and possibly limit it to the number of outer level caches. Runnable threads and non-blocked threads cause time slicing overhead. When a thread is blocked waiting for an external event such as mouse click or disk IO request, the operating system takes it off the round robin schedule. A helpful organizing principle is to separate compute threads from IO threads. Common useful practices are as follows. Let OpenMP do the work. OpenMP lets the programmer specify loop iterations instead of threads. OpenMP deals with managing the threads. Use a thread pool, which is construct used to maintain a set of long-lived software threads and eliminates the overhead of initialization process of threads for short-lived tasks. Expert may wish to write their own task scheduler. The method of choice is called work stealing, where each thread has its own private collection of tasks. Work stealing yields good cache usage and load balancing. Next is data races, deadlocks and live locks. This race condition consists of due to unsynchronized access to shared data. Program results are non-deterministic, depend on relative timings of thread, can be handled through locking. Deadlock. A problem due to incorrect locking results due to cyclic dependence that stops forward progress by threads. Live lock. Thread continuously conflict with each other and back off. No thread makes any progress. Solution. Back off with a release of acquired locks to allow at least one thread to make progress. Unsynchronized access to Shared memory can introduce race condition where the program results depend on non-deterministically on the relative timings of two or more threads. Races among unsynchronized threads. Parallel programming would be a lot easier if races were shown, but the same race can be hidden by language syntax in the variety of ways as shown in the figure. Update operations such as plus or is equal to are normally just shorthand and hence can result in interleaving. Sometimes the shared location is accessed by different expressions. Even if each thread uses a single instruction to fetch and update, the location there could be interleaving because the hardware might break the instruction into interleaved reads and write. The next slide gives about race condition hiding behind language syntax. Intel Thread Checker is a powerful tool for detecting potential race condition. It can see past all the varieties of camouflage which is shown in the figure because it deals in terms of actual memory location, not their names or addressing expressions. Sometimes deliberate race conditions are intended and useful. For example, threads may be reading a location that is updated asynchronously with the latest current value. In such situation, care must be taken that the writes and reads are atomic. Otherwise, garbled data may be written or read. The next slide is higher level race condition example. Data races can arise not only from unsynchronized access to shared memory but also from synchronized access that was synchronized is at too low a level. This figure shows such an example that intent is to use a list to represent a set of keys. Each key should be in the list at most once. If two threads both attempt to insert the same key at the same time, they may simultaneously determine that the key is not in the list, and then both would insert the key. Deadlock caused by cycle. Race conditions are typically cured by adding a lock that protects the invariant that might otherwise be violated by interleaved operation. Unfortunately, locks have their own hazards, most notably deadlock. This figure shows deadlock involving two threads. Thread 1 has acquired a lock A, thread 2 has acquired lock B. Each thread is trying to acquire the other lock. Neither thread can proceed. Though deadlock is often associated with locks, it can happen anytime a thread tries to acquire exclusive access to two more shared resources. Next gives the condition for a deadlock. This condition includes four which is hold true. Access to each resource is exclusive. A thread is allowed to hold one resource while requesting another. No thread is willing to relinquish a resource that it has acquired. There is a cycle of threads trying to acquire resources where each resource is held by one thread and requested by another. Deadlock can be avoided by breaking any of this condition. Often the best way to avoid deadlock is to replicate a resource that requires exclusive access so that each thread can have its own private copy. Each thread can access its own copy without needing a lock. If the replication cannot be done, that is in such cases where there really must be only a single copy of resources. Some wisdom is to always acquire the resource in the same order. The next slide gives about locks ordered by their addresses. If there is no obvious ordering of locks, a solution is to sort the locks by address. This approach requires that the thread know all locks that it needed to acquire before it acquires any of them. For instance, perhaps a thread needs to swap two containers pointed to by pointer X and Y, and each container is protected by a lock. And the thread could compare X less than Y to determine which container comes first and acquire the lock on the first container before acquiring a lock on the second container. The next is try and back of logic. The third condition for deadlock is that no thread is willing to give up its claim on the resource. Thus, another way of preventing deadlock is for a thread to give up its claim on a resource if it cannot acquire the other resources. For this purpose, mutexes often have some kind of try lock routine that allows a thread to attempt to acquire a lock and give up if it cannot be acquired. This approach is useful in scenarios where sorting the locks is impractical. This code sketches the logic for using try-lock approach to acquire two locks A and B, which is given above. This code has something timing delays in it to prevent the hazard of live lock. The live lock occurs when threads continually conflict with each other and back off. Next slide is heavily contended locks. Proper use of lock to avoid race condition can invite performance problem if the lock becomes highly contended. If threads try to acquire a lock faster than the rate at which a thread can execute the corresponding critical section, then program performance will suffer. A threads will form a convoy waiting to acquire a lock. Indeed, this behavior is sometimes referred to as convoy. The next slide is priority inversion scenario. This scenario tells like that some threading implementation allow threads to have priorities. Priority can be useful, but paradoxically can lead to situation where a low priority thread blocks a high priority thread from running. This figure illustrates priority inversion, continuing our analogy with software threads as cars and hardware threads as drivers. 3 cars are shown, but there is only a single driver. Low priority car has acquired a lock so it can cross a single lane critical section bridge. Behind it waits a high priority car, but because the high priority car is blocked, the driver is attending the highest priority runnable car, which is the medium priority one. In real life, this problem would be solved by bumping up the priority of blocking car until it is out of way, which with locks this called priority inheritance. When a high priority thread need to acquire a lock held by low priority thread, the scheduler bumps up the priority of blocking thread until the lock is released. An alternative is priority ceiling, in which priority called the ceiling is assigned to the mutex. The ceiling is the highest priority of any thread that is expected to hold the mutex. When a thread acquires the mutex, its priority is immediately bumped up to the ceiling value for the duration that it holds the mutex. The priority ceiling scheme is eager to bump up the thread's priority. In contrast, the priority inheritance scheme is lazy by not bumping up the thread priority unless necessary. The solutions for heavily contended locks. Upon encountering a heavily contended lock, the first reaction of many programmers is, I need a faster lock. Some implementation of locks are notoriously slow and faster locks are possible. The earlier discussion of deadlock mentioned the technique of eliminating a lock by replicating the resource. If each thread can have its own private counter, then no lock is necessary. If a total count is required, the counts can be summed after all threads are done counting. The partitioning can spread out contention among the logs. For example, consider a hash table implementation where multiple threads might try to do insertion at the same time. A simple approach to avoid this condition is to use single lock to protect the entire table. The lock allows only one thread into a table at a time. The drawback of this approach is that all threads must contend for the same lock, which could become a serial bottleneck. An alternative approach is to create an array of subtables, each with its own lock. In this figure, keys can be mapped to as subtables via hashing function. For a given key, thread can figure out which table to inspect by using hash function that returns a subtable index. Insertion a key commences by hashing and returns a subtable index. Insertion of key commences by hashing a key to one of the subtables and then doing the insertion on that subtable while holding the subtable's block. Pursuit of the idea of spreading contention among multiple locks further leads to fine-grained lock. And the next is hash table with fine-grained locking. If a data structure is frequently read but the infrequently written, then a reader-writer lock may help deal with contention. A reader-write lock distinguishes readers from writers. Multiple readers can acquire a lock at the same time, but only one writer can acquire it at a time. Readers cannot acquire a lock while a writer holds it and vice versa. Thus, the readers contended only with writers. This figure tells like the earlier fine-grained hash table is a good example of where reader-write locks can help if an array of buckets must be dynamically resizable. This figure shows possible implementation. The table consists of an array descriptor that specifies the array size and location. A reader-writer mutex protects this structure. Each bucket has its own plain mutex protecting it. To access a bucket, a thread acquires two locks, reader lock on the array descriptor and a lock on the bucket mutex. Next is non-blocking algorithm. One way to solve the problems introduced by the locks is to not use locks. Algorithm designed to do this called non-blocking. There are different non-blocking guarantees, that is obstruction freedom, lock freedom, wait freedom. Obstruction freedom. A thread makes progress as long as there is no contention, but live lock is possible. Exponential backoff can be used to work around the live lock. The system as a whole make progress. Wait freedom. Every thread makes progress even when faced with contention. Very few non-blocking algorithms achieve this. Non-blocking algorithms are immune from lock contention, priority inversion and convoying. Non-blocking algorithm has a lot of advantages, but with this come a new set of problems that need to be understood. Non-blocking algorithms are based on atomic operations such as method of interlocked class. This figure shows a wrong way and right way to decrement and test a reference count. In the wrong code, if the count was originally 2 threads executing the wrong code might both decrement the count and then both see it as 0 at the same time. The correct code performs the decrement and test as a single atomic operation. Thread safe functions and libraries. Defining a routine like foo that updates unprotected hidden shared state is a poor programming practice. In general, routines should be thread safe, that is concurrently callable by clients. However, complete thread safety is usually unrealistic because it would require that every call to do some locking and performance would be pathetic. This figure gives reference counted implementation of strings where the issue arises from the client's viewpoint. Each string object is a separate string object and thus thread should be able to concurrently operate on each object. In the underlying implementation, however, a string object is simply a pointer to a shared object that has a string data and reference count of a number of string objects that point to it. The implementer should ensure that concurrent access to do not corrupt the shared state. Next is memory issues. This memory issues consist of bandwidth, working in the cache, memory contention and memory consistency. Coming to this bandwidth, to conserve bandwidth, pack data more tightly or move it to less frequently between cores. Packing the data tighter is usually straightforward and benefits sequential execution. When declaring the structures in C or C++, declare fields in order of descending size. This strategy tends to minimize the extra padding that the compiler must insert into maintain alignment requirements as shown. Next is cache unfriendly sieve of Eratosthenes. This gives working in the cache Like data movement arises from the way that cores read and write memory. There are two categories of interaction to consider: those two cores and memory, and those between cores. This figure presents for enumerating prime numbers up to n. This version has two nested loops. The outer loop finds primes and inner loop inside function strikes out composite numbers. This version is unfriendly to cache because the inner loop is over the full length of array composite, which might be much larger than what fits in cache. This also explains about the code, which gives like shows how the sieve can be restructured to the cache friendly instead of directly representing the conceptual sieve as one big array. It represents it as a small window into the conceptual sieve. The window size is approximately root n bytes. The array striker stores the indices of these suspend loops and as element for each prime up to root n. Next is working in the cache. This figure shows the performance of differences. On this log plot, the cache friendly code has a fairly straight performance plot, while the cache unfriendly versions running time steps up from one straight line to another when n reaches approximately 10 to the power of 6. The restructured version is 5 times faster than the original version when n significantly exceeds the cache size, despite the extra processor operation required by the restructuring. Memory contention. This memory contention, the pattern corresponds to two types of data dependence: read-write dependence. A core writes a cache line and then different core reads it. Write-write dependence. A core writes a cache line and then different core writes it. If multiple cores only read cache line and do not write it, then no memory bandwidth is consumed. The array factor is read only once it is filled, thus each thread can share the array. The array composite is updated as primes are found. The updates are made to separate windows. The variable count is updated as primes are found. An atomic increment could be used, but that would introduce memory contention. A better solution as shown in this example is to give each thread perform a private partial count and sum the partial counts at the end. The array striker is updated as a window is processed. The striker induces a loop carry dependence between windows. For each window, the initial value of striker is the last value it had for the previous window. To break this dependence, the initial value striker have to be computed from scratch. The purpose of striker k is to keep track of current multiple of factor k. It keeps track of start of window for which striker is valid. This figure shows the multi-threaded sieve. A further refinement that cuts the work in half would be look for only odd primes. The next is fault sharing. The smallest unit of memory that two process interchange is a cache find or cache sector. Two hardware threads writing to different location content for a cache sector to a point where it becomes a ping pong game. This is a cache line ping ponging caused by fault sharing. This figure illustrates such a ping pong game. There are two threads, each running on different core. Each thread increments a different location belonging to the same cache line. But because the location belonging to the same cache line, the cores must pass the sector back and forth across the memory bus. Next is performance impact of fault sharing. This figure shows how bad the impact can be for a generalization of figure. For the above figure, 4 single core processor, each enabled with hyper threading technology, are used to give the flavor of hypothetical future 8-core system, each hardware thread increments a separate memory location. The I threads repeatedly increments. The performance is worse when the locations are adjacent and improves as they spread out, because the spreading puts the location into more distinct cache lines. Performance improves sharply at the stride of 16. This is because the array elements are 4-byte integers. Avoiding fault sharing may require aligning variables objects in the memory on cache line boundaries. Next is memory consistency. Consistency of variables when multiple threads access it. At any given instance in a time in sequential program, memory has a well-defined state. This is called sequential consistency. This diagram shows the current IA32 architecture. It approximates sequential consistency because it evolved in the single core age. Two rules for typical programming: relaxation for performance and strictness for correctness. A thread sees other threads reads and writes in a original order, except that read may pass a write to a different location. This reordering rule allows a thread to read from its own cache even if the read allows write to its main memory, which is explained by relaxation for performance, strictness for correctness. An instruction with a lock prefix acts as a memory fence. This slightly relaxed memory consistency is called processor order. The IA32 rules preserve more idioms but ironically break the textbook algorithm for mutual exclusion called Decker's algorithm. The key sequence in Decker's algorithm: two variables x and y are initially 0. Thread 1 writes x and reads y. Thread 2 writes y and reads x, which is explained in this diagram. Next is Itanium architecture. Itanium architecture, the model theoretically delivers higher performance than sequential consistency by giving memory system more freedom of choice. This figure shows a simple and practical example where the rules come into play. It shows two threads trying to pass a message via memory. Thread 1 writes a message into variable message and thread 2 reads the message. Synchronization is accomplished via flag is ready. The writer sets is ready after it writes the message. The reader busy waits for is ready to be set and then reads the message. If the writes or reads are reordered, then thread 2 may read the message before thread 1 is done writing it. Figure B shows how the Itanium architecture may reorder the reads and writes. The solution is to declare the flag is ready is volatile. Figure C gives volatile writes are compiled as store with release and volatile reads are compiled as load and acquire. Memory operations are never allowed to move downwards over release or upwards over an acquire, thus enforcing the necessary orderings. Shared memory without a lock. This figure gives the animals represents memory operation whose movement is constrained by animal trainers who represent acquire and release fences. The first idiom in message passing, which is generalized, a sender thread writes some data and then signals a receiver thread that it is ready by modifying a flag location. The modification might be a read or some other atomic operation. The second idiom is memory cache. Memory cache starts with an acquire fence and ends in the release fence. These fences keep any memory operation inside the cache from escaping. However, be aware that memory caches keep things inside from getting out and not vice versa. Avoiding pipeline stalls. Spin waits can be a problem because the spinning thread might consume all the hardware resources. In the worst case, it might starve the thread on which the spinner is waiting on the Pentium 4 processor and later processor. The solution to insert a pass instruction. This figure shows a spin wait with a pass instruction incorporated in most In more complicated weights based on exponential backoff, the pass instruction should go in the delay loop. And the last slide gives data organization for high performance. This program location is divided into four kinds of locality: thread private, thread shared and read only, exclusive access, Wild West. Thread private. These locations are private to a given thread and never shared with other threads. Thread shared and only. These locations are shared by multiple threads but never written by those threads. Exclusive access. These locations are read and written but protected by a lock. Wild West. These locations are read and written by unsynchronized threads. Thank you.